All right, so this is the second type of cone problem. You have a water tank that has the shape of an inverted circular cone. And you're like, what the hell is that supposed to be? It's so you just think ice cream cone, whose radius is half its height. This is not a throwaway line, it's there for a reason. Now, you're pouring water into the tank at a rate of 5 cubic feet per minute. Why cubic feet? Because it's volume. Find the rate that the water is rising when the water is 2 feet deep. Now, I'm going to try my best to draw the cone, right? It's a circular cone. The radius is here. It's a cone. So think ice cream cone. You're filling it with water. Here's your water. This is the height of the cone. So, you're filling it with water. I mean, it looks like crap, but that's the circular cone. Now, the volume, it's 1/3 pi r squared h. Why is pi r squared there? You have a circular cone. Remember, the area of a circle is pi r squared, but the circle constantly gets smaller as you go down, right? That's why you have this 1/3 in the h there. You have to account for the height of the cone, and the 1/3 is an offset for the fact that the radiuses keep getting smaller as the cone goes down. So remember what step one in this problem always was. Fill in everything that you know about this problem. So first of all, it says the radius is half the height. They don't tell you this for no reason, okay? Now, water is poured into the tank at a rate of 5 cubic feet per minute. They just told you something. The question is, what did they tell you? Okay. So I asked everybody what they thought that part meant, that water is being poured into the tank at a rate of 5. And everyone agreed that that's the change in the volume. When you are filling the cone with water, its volume is filling up. You're taking up the space inside of the cone. So that is the rate at which the volume is changing. So we're just going to put a 5 here. I don't care about the cubic feet. Like I said before, we're not in a physics class, so I don't care about the unit of measure. Now I want to find the rate which the water is rising. So you have two choices. That's either R or H, but water is rising up. So that is the height. So you are looking for dH dt. I'm looking for the rate at which the water is going up. The height of the water is changing. This is what I'm trying to find. So my formula is here. I'm given dV dt. I'm also given that the radius is half of the height. Now, I want to point something out. If you were to take this derivative right now, this is always step 2, right? Take the derivative with respect to time. If I take this derivative right now, I have a product here. I have r squared and I have h. If I use the product rule, right? First derivative, second derivative, first. I will end up taking the derivative of r, which will end up giving me a dr dt, which will completely screw me because I know nothing about this. I don't have this. There's no way I can use this. So my goal before I even do this step is to kill the r. I know that r, right, the radius is half the height. So I have to replace the r with h over 2. So before I can even do the derivative, I have to play a game of replacing r with h over 2. So I'm going to do that first. I need everything to be h, because if everything is not h, then I'm not even going to be able to take the derivative. Now I'm going to multiply it out. I have 1/3 pi. Now, how do you square this? You square the top, you square the bottom. H times h is h squared. And 2 times 2 is 4 times h. Now, I'm going to clean it up a little bit before I do the derivative. I have 1/3 and 1/4. That's a 12th, right? And then I have the pi. So you keep the pi. You may as well put the 12 on the bottom of it. And then you have h2 and h1, which is h3. So that's the formula that I'm going to take the derivative of. Now, obviously, I'm going to run out of room, so I'm going to have to erase stuff. So this is the formula that you now have. You have pi over 12 h to the third. I know this seems insane. You're like, there's no way I'm ever going to do this, but it's not as horrible as it looks. You basically just have to get rid of r. That is the reason that they told you this line. They gave you that line so that you can replace the r with h. And now you just have v and h. Look, they gave you dv, and you're solving for dh. There is nothing here about dr. R has to go. R cannot be there. So you're just basically substituting in for R and rewriting your formula. So R isn't there anymore. This is not a difficult thing to take the derivative of. What's the derivative of V? Well, it's dV dt, right? Now, what's the derivative of the other side? Pi 12 stays there. This is the coefficient of h cubed. It's like, it's constant, the derivative is 0. No, this is part of the h third, right? This is a product, so you can't just get rid of it. So pi 12 stays there. The derivative of h to the 3 is 3 h squared times dh dt. Now what I'm going to do is I'm going to knock the 3 into the 12. Just to simplify it a little more, since I'm running out of room, I'm going to pause this and erase it. Okay, so I erased it so I had more room to do this. As I just said, I'm going to put the 3 into the 12. You don't have to do this. It's just, you should. I mean, you have 3 over 12, which is a fourth. And then I have h squared dh dt. Now, I think in the beginning of the problem, I forgot to put, they told us that water was being poured into the cone at a rate of 5 cubic feet. So I put 5 there. They wanted us to find the rate at which the height is changing at the exact moment that the water was 2 feet deep. So they actually told me that h was 2. I don't remember if I wrote that in the beginning. I think I forgot. And then, so we're looking for dh dt. This is what we're solving for. We're looking for the rate at which the height of the water inside the cone is changing. So basically, I'm going to plug in everything I have, which is 5 and 2, and then I'm going to solve for this. So the volume is changing at a rate of 5. And I want to figure out the rate at which the height is changing at the moment that it's 2 feet deep. So you got to put 2 for h. And this is what I'm solving for. So now that's going to be 4. Oh, this is going to be super nice. 2 times 2 is 4. Now, I'm not going to be happy with you if you don't cross these 4s out. So cross out the 4s. And now just divide by pi. So we did all of that insane buildup. We rewrote the formula so that the r wasn't there anymore. All that work, and our answer was just 5 divided by pi. So that's it. All right, so I'm going to do 1b, which says the edges of a cube are expanding at a rate of blah, 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 blah. So I have a cube. Here's the volume of a cube, okay? It says, I want to know how fast the volume of the cube is changing. That's dV dt. This is what I'm looking for. It says the edges of the cube, I'm calling the edges x. It says the edges of the cube are expanding or increasing at a rate of 2. And I want to know how fast the volume of that cube is changing when the edge is 3. It makes sense. They have to tell me all this. I'm going to have a dv, a dx, and an x. So I need all that. So I have enough. So now I'm going to take the derivative. The derivative of v is dv dt. The derivative of x third is 3x squared times dx dt. Now I'm going to plug in everything I know, and that's going to give me this. I know that x is going to be 3. And I know that the edges are increasing at a rate of, it said expanding, but that's the same thing, expanding at a rate of 2. That's 9 times 3 is 27 times 2 is 54. So you write the formula for the volume of a cube. Remember, a cube, right? You're talking about x, x, x. Length, width, height. So x, x, x. It's a cube. It's like a square, just 3D. So all the sides are x. So that's where I'm getting x cubed. they would give you this formula, or I would give you this formula anyway, if you didn't know it. Take the derivative, plug in what you know. So this one was pretty easy. Again, don't worry about the units. Now I'm going to do the second one. Boop. So it says the area of a circle is increasing at a rate of. So as soon as I see that, I'm going to write the formula for the area of a circle. Area of a circle is pi r squared. Now it says the area is increasing at a rate of, so the area of the circle is increasing at a rate of 16 square inches per minute, whatever, I don't care about the units. Find the rate of change for the radius, that's dr dt, at the exact moment that the radius is 2. So they're telling you r is 2. And again, I only have 2 letters. I have A and I have R. So I have enough info to be able to plug in. I don't have to do any weird substitutions like you do with the cone. The problem with the cone is you have R and you have H. One of them has to go. Here, you don't have to worry about it. Just take the derivative. The derivative of A is dA dt. What's the derivative of pi r squared? Well, pi stays. You multiply it by 2. So it's going to be 2 pi r times dr dt. Remember the chain rule. Now I'm going to plug in what I know. The area, this time the area is changing at a rate of 16. So you put the 16 here. They tell you that the radius, I'm going to stop at the moment that the radius is 2. And I want to figure out the rate of change for the radius at that exact moment in time. So here you get 4 pi. Now you got to be, there is a very big mistake that I see people make here. I'm going to put this underneath there. So you get dr dt. I'm getting to the bottom, so I'm hoping I can still see it. Now, here, 16 is divisible by 4, and people will do this. Magically, the pi will go up there. You could put 16 divided by 4, but you have to make sure that pi stays on the bottom. So the answer is 4 over pi, not 4 pi. So be super, super careful.